So in the previous section, we talked about the equilibrium constant and the equilibrium constant expression here, Kc, in concentration. And I said shorthand, we call this products over reactants, remembering that everything is raised to its stoichiometric coefficient, as shown here. So what about the relationship between the Kc of one reaction and the Kc of another? Well, what if we wanted the Kc of the reverse reaction? So in this case, we are assuming that A and B are the reactants and C and D are the products. So when we put products over reactants, it looks like this. But because this is a reversible reaction, we could just as easily assume that these are the reactants and these are the products. In which case, we would put A and B on the top and C and D on the bottom. Said another way, the Kc of the reverse reaction is 1 over the Kc of the forward reaction. So we have to take the reciprocal because we flip what's on top and what's on the bottom. What about a multiplication factor? Let's say that we wanted to double this reaction. So 2 of these, 2 of these, 2 of these, and 2 of these, assuming they're all 1 to begin with. Well, if we were going to double all of them, we would have to double all of the exponents. In order to double the exponents, we need to raise this power to the n. So the Kc of the new reaction with a multiplication factor, double, triple, halved, whatever, okay, is the Kc, the original Kc, raised to the n power, where n is the multiplication factor, double, triple, whatever the case may be. It still has to be balanced, so you have to double everything or triple everything or halve everything. You can't just double or triple one of the products or reactants because then you won't have a balanced chemical equation. So let's look at a few examples where we actually use these relationships between different Kc's and write Kc expression constants. So it says, given the following reaction, what is the expression for Kc? So if we write here, Kc equals products over reactants. So product, concentration of Hi squared divided by concentration of H2 to the 1, concentration of I2 to the 1. So this is the equilibrium expression for this reversible reaction here. It says if the equilibrium constant for this reaction is 1 times 10 to the 4, are the products favored or the reactants favored? Well, 1 times 10 to the 4 is far greater than 1. So since it's far greater than 1, it means we have a bigger number on the top and a smaller number on the bottom. The top is the products, so the products are favored. The next question says, what is the equilibrium constant for the reverse reaction? Now it doesn't want this expression for it, it wants the actual value of the equilibrium constant. Well, if you remember from the previous slide, the Kc of the reverse reaction equals 1 over the Kc. In this case, it's going to be 1 over 1.4 times 10 to the 4. And when we do that, we get 7.1 times 10 to the minus 5. So here we have found the new value of Kc. And I haven't mentioned this before, but Kc's are generally reported as unitless, all right? So there's no units here and there's no units here. So this is the new value of Kc because we have the reverse reaction. Essentially, we flipped this over, so we had to flip this over. Next one says, what is the equilibrium constant for half of the reaction? So we have half of H2 plus half of I2 yields Hi. A little weird to have halves in here, but we can still do it. So remember that Kc of the multiple, I'm just going to put it that way, equals the original Kc to the n. In this case, it's the n is half because we halved everything. So the original Kc, okay, up here is 1.4 times 10 to the 4. And we need to raise that to the 1/2. Said another way, we need to take the square root of it. And when we do that, we get 118. So if we half everything, all these powers change by half. So if we take the square root of this, in this case, or raise it to the half, we get the answer. The next one is a different reaction. It says if the equilibrium constant for the reaction below is 8.2 times 10 to the minus 2, or just as it is. All right, and here we have the reaction. What is the equilibrium constant for this reaction? So we have 3x 2y plus 6 yields 6x plus 3y. Well, we have to notice what we did with this reaction compared to this reaction. The first thing I notice is the product is now the reactant. So we reversed it. All right. So we want to take 1 over the Kc in order to find what the value is because we reversed it. What else did we do? Here we have 2, here we have 6, here we have 1, here we have 3, here we have 1, here we have 3. We also tripled it. So we need to take that and we need to cube it. So we need to take 1 over it and cubed it. So we have the Kc value, so we take 1 over 8.2 times 10 to the minus 2, and then we cube that value, and when we do all that work, we get 1.8 times 10 to the third power. Okay, so these are some mathematical relationships between one Kc and another, depending on the differences between the two reactions. So what's important is we find what the difference is between the two reactions, and then we just perform the mathematical operations in order to do that. So now we want to look at more lecture notes. So there is a relationship between Kp and Kc. You'll recall that Kp is for the gases, the pressure of the gases in atmospheres. Kc is for the concentration in molarity. And the difference between them is this RT delta N, where R is the ideal gas law constant, 0.08206 liter atmospheres per mole K, not in joules per mole K like in the previous chapter. And we're going back to the ideal gas law constant in liter atmospheres per mole K. And temperature, or T, is the temperature in Kelvin, where Kelvin is C plus 273 or plus 273.15. Delta N is new, and delta N is the change in total moles of gas. So if you have a reaction with 3 moles of gas on one side and 2 moles of gas on the other side, you've lost a mole of gas. So it's the total moles of the gaseous products minus the gaseous reactants. So it's products minus reactants in order to find that. So I think that instead of explaining this in great detail, it'd probably be better to do this also as an example. So here we have an example where we want to convert Kp and Kc. So we have the reaction that we just talked about, which is Kp equals Kc times RT to the delta N. So the first thing we want to find is delta N. So delta N is product moles minus reactant moles. Now in this case, in both these examples, everything is a gas, so it's just total number of moles. But you would need to be careful, because if not everything is a gas, it's only the moles of gases that count here. So in this case, on the product side, we have 1 mole of gas, X2Y, but there's only 1 mole of gas. And on the reactant side, we have 2 X's and a Y, or a total of 3 moles of gas, which means that we lost 2 moles of gas, right? We had 3, now we only have 1, so we lost 2 moles, and delta N is minus 2. Well, now we can plug in. Kp equals Kc, okay, which is, in this case, in this case we're given the Kp and we're looking for the Kc. So let me write this out again. Kc times RT delta N. So in this case, we're looking for Kc. So we divide by RT delta N, and we divide by RT to the delta N. I should write it like that. All right, cancels out on this side. So Kc equals Kp over RT to the delta N. Plugging in, we have the Kp, which is 5.44 times 10 to the minus 2. We have R, 0.08206, that's liter atmospheres per mole K. We have T, which is already given in K, so 398 K. And we know that delta N is negative 2. When we do this math, we end up with 58.0 as the value of Kc. So they're quite a bit different in this case, right? 0.0544 versus 58. Why are they so different? Because we had a relatively large change in moles, right? We lost 2 moles of gas, which when we only had 3 to begin with, is a large change in the number of moles. Let's look at another example. Okay, in the second example, it says find the value of Kp for the reaction below if Kc is 8.65 times 10 to the 3. So we're going to use the same equation. Kp equals Kc RT to the delta N. Well, let's find delta N. Delta N on the product side, we have 2 moles. And on the reactant side, okay, we also have 2 moles, which means delta N is 0 moles. No moles of gas changed. So what we have is Kp equals Kc times RT to the 0. Well, what is RT to the 0 going to be? Any number raised to the 0 power is 1. So Kp equals Kc times 1. Or Kp equals Kc. So since Kc is 8.65 times 10 to the 3, Kp is also 8.65 times 10 to the 3. When the moles of gas don't change, all right, from products to reactants, Kp and Kc are equal to each other. Do you need to do all this math to figure this out? No. Once you realize the two don't change, there's 2 moles on this side and two moles on this side, you can basically just know that this is the value of Kp and Kc. All right, switching back over to the lecture notes here. The next thing we need to look at is heterogeneous equilibrium. And what is a heterogeneous equilibrium? Well, a heterogeneous equilibrium is an equilibrium which has things that aren't gases or aqueous, all right? Things that are gas or aqueous are going to be in our equilibrium constant expression. In this case, H plus and HCO3 minus, okay? Protons and bicarbonate ions are in our equilibrium constant expression. They're both aqueous, so products on top. Reactants, CO2 is here because it's a gas and it has a concentration. But solids and liquids, in this case water, which is highlighted red here, is not in this. And one way to think about this is that as long as there's some of this liquid and solid present, they have functionally the same concentration. So their concentration is a constant, and we ignore them in the equilibrium constant expression. Okay? And so we don't write them. That's the take-home message here. If you see a liquid or a solid, you do not put it in the equilibrium constant expression. And if you're calculating equilibrium constants, it's very important that you don't put them there. That being said, if you're given a problem, you're probably not going to get a concentration for water, okay? So that's a pretty good hint that you could ignore that. So let's take an example here and solve this one out, okay? It says, what is the equilibrium constant for the following reaction if at equilibrium the concentration of CO2 is 1.4 molar, the concentration of H plus is 0.22 molar, and the concentration of bicarbonate is 0.22 molar. So the first thing we want to do is we want to write the equilibrium constant expression. Kc equals, now it's products over reactants. So concentration of H plus times the concentration of HCO3 minus over the reactant concentration of CO2. And as I mentioned before, you're not given a concentration of water here, but the concentration of water is not in the equilibrium constant expression, which is a good hint, right? If you're stuck on a question on a test or something. That being said, we can write the equilibrium constant expression this way, and now we have all the values. Note that these are equilibrium concentrations. Later in this chapter, we're going to be given initial concentrations of some of these things, and then maybe the equilibrium concentration of a product, or maybe not. So we'll see some examples like that. But in this case, we are given equilibrium concentrations, so we can just plug these numbers in. So H plus is 0.22 molar times HCO3 minus, which is also 0.22 molar, divided by the concentration of CO2, which is 1.4 molar. All right, and I'm ignoring units because these K values don't usually have units. And when I do all that math, I find that Kc for this particular one is 3.5 times 10 to the minus 2. Okay. Next one. It says, at a certain temperature, the reaction below has a Kc value of 1.8 times 10 to the 2. If at equilibrium the concentration of Y is this, and the concentration of X2Y is this, what is the value of the concentration of X in the equilibrium mixture? So same thing as before, we need to write our equilibrium constant expression. So products over reactants. Kc equals the concentration of X2Y divided by the concentration of X squared times the concentration of Y, like so. Plugging in. Kc, we know, 1.8 times 10 to the minus 2 equals the concentration of X2Y is given in the problem, 0.84. The concentration of X squared is our variable, that's what we're looking for, and the concentration of Y is given to us as 0.028, like so. Okay, so now we got to simplify this. The easiest way to do that is to cross multiply. So we take this number times this number, and what we get is 5.04 times the concentration of X squared. So the X squared just comes along for the ride, and we multiply this times this, equals 0.84, which is still left on this side. Divide by 5.04, divide by 5.04, and we find that the concentration of X squared is equal to 0.17. How do we get rid of the X squared? We take the square root. Take the square root of both sides, and we find that the concentration of X is equal to 0.41. Note that it would be plus or minus 0.41, but a concentration of negative 0.41 molar doesn't make any sense. So the concentration of X is 0.41 molar. Okay, typically we might put the unit back at the end like this, because it actually asks us for the concentration of X, but I don't typically write out the units in these calculations because they're not the same every time, and then you have to keep track of them. Like here you'd have molarity cubed if you were given molarities here, and you'd have a molarity up here, and then you have to keep track of all that, and it just makes it a little bit cleaner, I guess you could say, if you don't use the units. Not to say that it's wrong to use the units, and maybe it's even better to use the units, I don't know. All right, let's look at the last type of example that we want to look at in this section. The last thing that we want to look at is the reaction quotient. So the reaction quotient allows us to predict which direction the reaction will shift based on the equilibrium constant. So if you look here, we have Kc and Kp, all right? And Ks are at equilibrium. So once the rate of the forward reaction and the rate of the reverse reaction have been established, right, or it's reached equilibrium, then we calculate these values. Q is mathematically the exact same thing, but the difference is this could be at any time, right? When you first start the reaction, 1 second later, assuming the reaction doesn't only take 1 second to reach equilibrium, it's not going to be at equilibrium, and you're probably going to have more reactants than you have products. So what this allows us to do is tell which direction the reaction is going to shift at any given time based on the values that are present. So there's a couple things to note, okay? If Q is greater than K, okay, the reaction is going to proceed in the reverse direction. If Q is bigger than K, it means the numbers on the top are the bigger numbers. Said another way, we have too much products in the reaction mixture. So the reaction is going to shift to form more reactants. So you could say it proceeds in the reverse direction towards the reactants, or you could say there's extra products. This is basically the same thing. What if Q is less than K? Okay, in this case, if Q is less than K, it means that A and B are a bigger number than they should be at equilibrium. So it means you have extra A and B. This is like the reaction 1 second after it starts if it takes more than 1 second to reach equilibrium. These reactants are in too great of concentration, so they proceed to form more products. Said another way, the reaction shifts towards the products in the forward direction. Finally, what if Q equals K? Well, if Q equals K, then the reaction is currently at equilibrium. So the only difference between K and Q is when. K is always calculated at equilibrium. Q can be calculated at any time point. But then we can compare the values to find whether we have extra products, whether we have extra reactants, or whether the reaction is already at equilibrium. So let's do an example of this, and this will be the last one for this section of the course, or of the lecture. It says, for the reaction below, at a certain time, the concentration of CO2 is 1.38 molar, the concentration of H plus is 0.36 molar, and the concentration of HCO3 minus is 0.48 molar. And then it gives us the equilibrium constant. Which direction will the reaction proceed under these conditions? Well, the first thing is we want to write the expression for Q. All right, Q, QC, okay, like this. So what is the expression? It's still products over reactants. Concentration of H plus, concentration of HCO3 minus over concentration of CO2. All right, this is exactly the same thing as the expression for Kc. The only difference is Kc was calculated when the reaction was at equilibrium. Qc is calculated for these specific conditions as given in the problem. So let's look at Qc again. We have the concentration of H plus, which is 0.36. Okay, we want to multiply that by the concentration of HCO3 minus, which is 0.48. And we want to divide that by the concentration of CO2, which is 1.38. When we do that, we find that it's 0.125. So now let's compare these values. Is 0.125 greater than or less than 5.3 times 10 to the minus 3? Well, this number, even though it's a small number, it's still bigger than this number. So it is greater than 5.3 times 10 to the minus 3. Said another way, Q is greater than K. So if Q is greater than K, it means that we have too many products for the reaction to be at equilibrium, right? Because products are on the top, it means there's extra products, there's extra V's. Well, which direction is the reaction going to shift when we have extra products? The reaction is going to shift to the left to form more reactants or to get rid of the products. So in this case, the reaction shifts left. All right, so it shifts to the left, and we could say this is to form more reactants. All right, or we could say to remove excess products. Excess relative to equilibrium conditions. Okay, right now the reaction isn't at equilibrium. The reaction wants to be at equilibrium, and it's not because it has excess products, and therefore the only way it has to get rid of those products is to convert those products back into reactants. So in this section, we kind of went through a hodgepodge of a bunch of different types of problems that you can do related to equilibrium. In the next section, what we will look at is the relationship of these equilibriums and what we can do to disturb the equilibrium. Like what would happen to the equilibrium here if I added more CO2. Okay, how would how would the reaction shift in that way? And then in a later section, we'll look at, well, how do we find values of K if we don't know the equilibrium concentration of something? Let's say we know the initial concentration of this, but we don't know the equilibrium concentrations of this.